Okay, today we will be working on problem 5.19. Specifically, this one is related to transient problems. So getting right into it, the problem statement in the book says a plain wall of a furnace is fabricated from plain carbon steel. It gives you the properties of that carbon steel, and then the thickness of the wall, which is 15 millimeters. And then adds to protect it from the corrosive effects of furnace combustion gases. One of the surfaces is coated with a thin ceramic film. This is shown right here in this little schematic down here. And then that says that that film has a thermal resistance of 0.01. And then the opposite surface is well insulated from the surroundings, so we don't really need to worry about that. So then it finishes up saying at furnace startup, the wall is at an initial temperature of Ti equals 300 K or Kelvin. So that's our initial temperature. And then the combustion gases are 1300 Kelvin that enter the furnace, providing a convection coefficient of 30 watts per meter squared Kelvin at the ceramic film. Assuming that the film has negligible thermal capacitance, it's asking for how long will it take the inner surface of the steel to achieve a temperature of TSI equals 1000 K. And then it finally asks what is the temperature TSO of the exposed surface of the ceramic film at this time. So that's that temperature out here. So jumping into that, I have written my given statement. So it's just all that stuff again, kind of more compact. And then find, I wrote these out of order on accident, but it wants the time taken to heat up to that temperature, and then the TSO from that layer out here. So here's a schematic again, basically the same from the textbook. And then for our assumptions, it mentioned that the film has negligible thermal capacitance. And then I also just wrote down some basic ones like constant properties, and that it's a transient problem. So beginning with the analysis, I'm trying to make sure that you can't really see the solution just yet. So first we have to check the Biot number. Basically, that determines what kind of transient solution we're following, so whether it's a lumped capacitance or first term approximation. So here you can see I use the 30 watts per meter squared Kelvin for my H value, and then the thickness of 0.015 meters. That's the 15 millimeters, and then 60 watts per meter Kelvin for K. And that came out to 0.0075, which is obviously less than 0.1, so we are going to use a lumped analysis. Now, when looking at this problem, we have one resistance that's going to be used later on. So I just wrote it in, or sorry, two resistances, one being the convection and then the other one being that that film resistance that they gave us. So U is equal to the reciprocal of R total. So R total is then 1 over H plus our resistance for the ceramic film. And that turns out to be 23.08 watts per meter squared Kelvin. We'll use that later within probably like the next one or two steps. I think I see it right down here. Yeah. So it's good to get that one out of the way. So then our next equation from our textbook, I can pull it up here. We see the difference of the base temperature and the temperature that we need. So I actually can't find it in the textbook. Sorry about that. Here we have a little bit. We have the denominator of it, but here we see that the temperature that we are currently analyzing, the ambient temperature and then the base temperature, once again, the ambient temperature, and that's all equal to e to the negative t over our time. What is that term? Sorry, I'm forgetting that term. The name of the term at least. It's very important though that we need to solve for that, which I did. I just can't quite remember the name of the term. Apologies for that. But we're just gonna move on from that for time reasons. So from here, what I did was I just solved first for negative t over tau. So that's negative t over r times our c value, which was given to us before. If you want to break that down even more, we can then solve it for using u t over density times our length or the thickness times the c. So I did just that, and I found that term multiplied by t. So then I plugged in all the values back into that equation. So our initial temp or our temperature of the inside wall, 1000 Kelvin, minus the 1300, the ambient temperature, over our initial temperature, 300 minus the 1300. And that's all equal to e to the term that we just found. So then it turns out that in order to get to that temperature, starting from 300, it would take 2,640.29 seconds. So that's the answer to the time taken to get to that temperature. Now we must find TSO. So doing that, just that, we know that through boundary conditions, we'll have Q is equal to uh, just the, or from thermal resistance, we have the difference of temperature TSI over or minus TSO, and all of that is over just that resistance of the ceramic film, and that's equal to Q. Uh, and also, since it is 1D, we know that Q is going to be equivalent to our convection coefficient times the change or difference in temperature from ambient to the surface temperature here. So I did just that. We have h time T infinity minus TSO, and then that's equal to the difference of TSO minus TSI over the resistance. So our unknown is TSO. So in order to find that, we have the two terms here. We just have to do some algebraic manipulation. And then we get to a equation here, which says TSO is equal to h times T infinity plus TSI over RTF, and that all of that over h plus 1 over RTF. So then I just followed in by plugging all the values in, and we get a outside temperature of 1069.23 Kelvin. So that's the problem. I'm sorry that I blanked on some of the terms, but they're just defined here with the equations. You can find the name of these terms in the textbook. It's just been a long time since I've actually seen those again, so I kind of forgot them. But yeah, so that's that solution. Thank you.